Unit 3, Lesson 2, Scale of the Solar System. So, the main idea behind this lesson is if I was to tell you to draw a scale drawing of the universe, or of the solar system, I should say, let's go a little smaller, um, is basically impossible, right? Like, you're going to need a lot of pens and pencils in order to draw that large, right, solar system. So this is where scale drawings come into effect from lesson 1. So how do we get things to be scaled if you were to draw small representations, right? So how would you do that? Like you have, several planets, right? And they're all going around the sun, and it's like, okay, well, how big do I want the sun to be, right? And then how far away is the first planet, right? So maybe it's that. That's actually probably way too close if you think about it. That pretty sure that planet will be toast. Maybe a little bit further out. So now it's like, okay, scale is a big problem. Maybe there's another big planet like further out. So it's like, how would you draw a scale representation uh, so you can actually draw the solar system? So let's look at 2.1, solar eclipse. And in this one, well, first off, I should say 2,000 years ago, your average human being walking around would stare up at the sun, of course, burn their retinas out in the process, but they would look up at the sun and go, wow, that's just a small little tiny, light. Like it's just right up there. If I had a tall enough ladder, I can get to it. That's literally what most of them were thinking, except one guy was walking around just shaking his head, going, no, it's just really, really far away. And they're like, I don't know. Pretty sure I can get a big enough ladder. so so um, basically the idea here is if we're going to go off of the dimensions of the sun, right? And they tell us, the sun here is what? 1.3. That's a horrible line. I don't know what happened there. So what 1.3 million and some change, right, for the diameter, right? And they tell us that the moon's diameter is a little bit more adorable. It's just 3,475 kilometers. It's not too bad, right? Especially compared to the sun. It's like that's huge, right? Um, they tell us the distance from the Earth to the sun. Okay, so let me write that. There to there. It's 149,600,000 kilometers. Thank goodness. All right. So they tell us the distance is that. Now, they're asking us is how far away does the moon need to be to where the moon looks like it's the same size as the sun itself, right? So that's their question. Now, how do we do that? Well, we have to set up a proportionality statement. Okay, so our concern, what we're trying to find, is the distance of the moon, right? And that's in relation to its diameter. And we're comparing that to a similar situation where you have the distance of the sun. And let me go ahead and we're not dealing with numbers yet. I don't know why I'm so eager to do that. So we got the diameter, right, of the moon. So the distance of the moon in relation to the diameter of the moon should be proportional to the distance of the sun and the diameter to the diameter of the sun. Okay, so let's go ahead and use this proportionality statement to figure out how far the moon needs to be in order to look like the same size of the sun. So the distance of the moon, we don't know. Okay, x. We do know the diameter of the moon to be 3475, right? Kilometers. And the distance of the sun is some ridiculous number, 149,600,000 kilometers. And that's, again, into the relationship of the diameter of the sun, so which was a little more adorable compared to its distance, thankfully. Distance is important because we don't want to burn up. Just kind of look at some hotter planets. Now, let me get the big boy calculator out because we got some serious numbers to do here. All right, so for those who are watching, again, when we're solving for x, we're cross multiplying. So I know you guys are sophomores, most of you. Cross multiplication, right? I know in middle school, some teachers will draw the adorable butterfly, and that's how a lot of kids remember it. So we're going to go ahead and multiply the 3,475 kilometers times the 149,600,000 kilometers equals some ridiculous number, like it's in the billions, and then divide by the 1,391,000. You guys ever type too fast and you're like, oh, did I press the wrong button? No, I think I'm good. There we go. So you should get x to be, or the distance from the moon, right, to be 373,731.128. Let's go ahead and round up 7 kilometers. All right, so so this is the tenths, hundredths, thousandths, 10,000th place, just because whenever I think about distance in astronomy, I always think of in respects to trying to land on the planet or the moon or whatever celestial body, except the sun. I'm not landing on that. Nope, not going near that. I want to stay really far away from that. All right, so that's how far the moon needs to be in order to look just like the same size of the sun. Okay. All right, so that's a proportionality statement. All right, so proportionality, if I can fit it over here. So let me move things down. I always feel like I have a lot of room and until I don't, right? So this is a proportionality statement. Okay, and that's what gets me my setup. Okay, so distance to the moon to its diameter, distance to the sun to its diameter. They should be proportional. Yes, they're two different planets, but in this situation, we're trying to figure out what distance will the moon need to be in order to look like it's the same size of the sun. Okay. All right. So that's your first example. Now in this one, basically it's saying here's all this information about your other planets, and they're basically saying a circle. If you were to draw this, your circle with a 2 centimeter diameter will represent Earth. That means the 12,756 kilometer diameter given on that table is just 2 centimeters. So like if you were to go outside with chalk, and you have this huge basketball court, you would draw just a tiny little circle, 2 centimeters with diameter, with chalk, and that would be Earth. Okay. Now you're trying to figure out, well, if I'm shrinking Earth down to that size, to that scale, what's the diameter for all the other planets? And then notice how they also give you the average orbital radius, right, of all the planets as well. So it's like, okay, well, what are those going to be? Like and that's really how far apart they are going to be from the sun, right? So like if you were to draw this with chalk, you'd be like, okay, uh, like here's the sun, right? Mercury's like over here. Venus is a little bit bigger, right? Uh, Earth is like pretty much the same size as Venus almost, right? Just a little tiny bigger. And then, so basically that's what the table's doing, right? And the orbital radius is, their path around the sun, right? Um, so that's kind of what they're doing here. Now, how big are these objects going to be? How far are you going to space these planets out from the sun? Well, if, again, our scaling creates that's given to us, right? So let's go ahead and create proportionality statements to solve the rest of the planets. So first things first, let me go ahead and start by finding out how many centimeters the 149,600,000 kilometers would be. So how do I do that? This is what I would do. Okay, again, we're looking for how many centimeters, right, for the orbital pattern for Earth. We know that in kilometers, it's this many millions of kilometers. And we know that 2 centimeters represents the 12,756. So I'm just going to cross multiply with my calculator, the mutilator of numbers. And I'm going to go ahead and multiply the 149 million, 149, 600,000, there we go, times the 2 centimeters, divide by the 12,756, and we get 23,455.6 kilometers. Okay, if you do that, let me move it a little bit more. There we go. There we go. All right, so that's actually not kilometers. My bad. Remember, that's centimeters. The 149,600,000 kilometers is actually 23,455.6 centimeters. So if you were to draw that on the chalk, with the chalk on the basketball court, you'd probably be like, oh, that's a lot. Like I might need a bigger basketball court, right? So that's kind of like a realization. Maybe your scale factor isn't small enough. You know what I mean? So it would be an interesting thing to do if you really are bored. Okay, so what I want you to do, all right, this is for you. I want you to find 2 planets, all right, their diameters and their orbital or orbit radius. Okay. You can use the given scale factor. Okay, so for example, with Mars, okay, I'll go ahead and find the diameter for Mars. Okay. So diameter is 6,792. And again, I'm going to use the same scale that was given to me from Earth, which was at 2 centimeters, is 12,756. You can actually use that ratio there, that scaling, for every single one of these. Okay, cross multiply. So get the calculator out. 6,792 times 2 equals, make sure you guys press equals before you press the divide. Okay, be careful if you're using your iPhones. All right, so divide that by the 12,756, and voila, 1.06 centimeters. Okay, so as you can see, Mars is actually a lot more adorably tiny compared to Earth. Okay, so I want you guys to find other planets. Don't worry about Earth. Don't worry about Mars. Don't need to worry about that because I kind of touched Earth and Mars. You guys go explore the rest of the solar system. Just 2 planets, right? You pick your 2 and just uh, email me your answers or send me your or turn in your notes with those 2 answers. That'll work. Let me look, make sure I'm not skipping anything. What information do you need in order to draw the planet and place it accurately on the sun? Right, everything in the solar system is revolving around the sun. We tried to burn the first human who was saying that at the stake until a tyrant came in and saved his life. And who said tyranny was horrible? Lorenzo de Medici was awesome. You guys wouldn't have the movie Godfather without Lorenzo de Medici. All right, so, or Medici. I can't remember how they pronounce it. Your teacher will give you some information. I'm not having you draw this because, well, you're going to need a bigger piece of paper to do that. Yeah, because that's going to add up. All right, so that probably would happen, right? Like you draw that on a piece of paper and you wouldn't fit everything on there. Okay. Um, until you probably do something like this, or you imagine the Earth is about the size of this little period, right? Which is about 0.3 millimeters. All right, so how big is the scaled version of your planet now? Well, notice they changed it on us, right? So they just made everything super small. So what would that do for all your other measurements? All right, so same situation, just different scale. Find 2 planets. Okay, but now you're using that new scaling that they give us. Okay, the 0.3 millimeters. So for example, I'm going to find the average orbital radius for Earth using that new scaling they gave us. So let's do that. Notice I'm setting it up to where it's like, okay, what's going to be my new measurement if it's 149,600, I'm sorry, 149,600,000, right? If 0.3 millimeters is 12,756. All right, so let me get my calculator again. Cross multiplication, 0.3 times 149,600,000. Really making sure I don't mess up on that. Divide by the 12,756, and you get 3,518.34 millimeters. Wow. How far is that? Like, that's actually pretty far still. Like, I know what, 10 millimeters looks like, but dang, 3,518, that's still a pretty good distance. All right, so that's all I want you to do. Pick 2 planets, use this scale, all right, that they gave us. And as for the questions below, How big is the scaled version of your planet now? Well, you pick a planet. Pick a planet. Find two of them. All right. Find the diameter and the orbital radius. How far from Earth is it? Oh, that's pretty important. Just find me the new measurements for your planets. Okay, that's good enough. And then can the scale drawing of the solar system fit in a classroom now? Um, maybe, maybe not. I think you'll be able to fit half of it, depending on the size of your class. Okay, so lesson synthesis, as you can see, that's not really a scale drawing, right? Like planets aren't that close together. They're way out there. What's really crazy is how big Jupiter is. They actually say that because of its mass, it actually protects Earth from asteroids flying through. Because apparently it changes their trajectory so much, they just swerve out and away from Earth. So that's actually factored in when we look for life on other solar systems. It's like, do they have a big planet that moves things and protects them? It's like, oh, we got to look that up too, because any planet can have water and be in the Goldilocks zone, but do they have a gas giant protecting them? So okay, have a beautiful day. Thank you.